halogenation reaction, or the radical halogenation reaction of alkanes. So we're talking about radical halogenation of reaction of alkanes. We know what alkanes are. There's a huge variety of them. You were busy drawing constitutional isomers and learning nomenclature with these things. So alkanes we know quite a bit about. They're the simplest possible organic molecules. The only function group they have are sp3 hybridized carbon, and all carbons are attached to either carbon or hydrogen. This is an example of a substitution reaction. And actually, acid-base chemistry is an example of a substitution reaction. We're going to learn about a couple other types of reactions, like elimination and addition later, but a substitution reaction, the most basic fundamental way or parts that we look at is A plus B give things like C and D, where parts of A and B exchange with one another, and then they make something new. C and D, for example. So parts of A and B, they switch places and we get new things. We call these C and D. It's called, in general, the most basic terms, a substitution reaction. Okay? These reactions will be called radical reactions because, as you're now aware, they're going to involve unpaired electron, this kind of weird thing that you didn't really do too much, especially with early efforts and endeavors in Lewis structure drawing. You're always drawing pairs in, as I mentioned, but we're now going to be dealing with a single electron. We'll talk about it as we go. The first reaction we're going to spend most of our time with is the reaction of methane plus X2, where X could be F, chlorine, bromine, or iodine. Okay, so the reaction is actually quite simple. We're just going to look at methane and think about fluorine, chlorine, bromine, and iodine. There's something I need you to know about these particular atoms, and you're going to be happy about it momentarily. When we use fluorine, the reaction is actually very dangerous and we get explosions. There's no way that I'm teaching you that reaction. I don't have enough liability insurance to cover myself in case you guys go out and start fluorinating things. Chlorine will be a reaction that will be very important. It'll be our most important one, and bromine is going to be a point of contrast. And it turns out for iodine, or I2, the reaction, no reaction takes place. So I want you to know this particular trend, that F is very reactive, or F2, and I2 is unreactive, and chlorine and bromine are the two sources of halogen that we'll be working for. So this is convenient. Our life's getting simple already. We're down to just methane and chlorine or bromine. And the first reaction we're going to look at, you already saw and have a preview of. If we take methane and chlorine and we mix them at room temperature, nothing happens. These two things are both gases. You can imagine filling a flask with some gases, capping it, and you can sit there and wait for 3,000 years. Nothing's going to happen with these things. But the second we either shine UV light or heat this reaction, let's say to 250 degrees Celsius, pretty high. So if we either shine UV light on this or heat it to 250 degrees, we start getting a reaction, and that reaction that takes place is a radical halogenation reaction. The halogen we're using in this case is chlorine, or Cl2, and so this is a radical chlorination reaction. And if this is a little tricky or hard to see, this is chlorine. It's the way I write it, usually kind of this weird cursive Cl and Cl, so that it looks different than carbon. You can also tell it's chlorine because we have these pairs of electrons surrounding it. So this is clearly a substitution reaction. We mix A and B. Some of their parts switch and mingle, and then we get C and D. We can see that a hydrogen on methane has been substituted with chlorine. And on Cl2, we can see that chlorine, one of the chlorines, have been substituted with hydrogen. So this is the textbook definition of a substitution reaction. It's just a very, very generic type of term to define reactions that switch parts with one another. Again, I kind of previewed the fact that we'll talk about addition and elimination reactions later. But for now, this is a substitution reaction. We have two reactants, two products. So how does this reaction work? We mix chlorine and methane together, and I've drawn them out in their full Lewis structures. And the values and energy values that I'm about to give you in our lecture notes, they always differ just a little bit by different energy tables. Don't get fixated on that. These energy values you don't need to memorize. When I ask you to use these types of energy values in a very modest way on our second exam together, I'll give you only the energy values you'll need for a problem. But for now, the bond association energy, or the strength of this particular bond, and the strength of this particular bond are known. And for sp3 hybridized methyl group, it's about 100 kcals per mole. That's a number that probably doesn't mean much to a lot of you. I get it. Don't worry about it. And chlorine is 60 kcals per mole. So we can at least tell that the chlorine-chlorine bond is weaker than the carbon-hydrogen bond. That's all we need to know with this, what these numbers mean. And so I want you to think, if we heat these two things up to 250 degrees, we start putting a lot of energy into the system. Which one of these bonds is going to break first? And it's kind of almost a rhetorical question. It's simple, that the weaker bond will break first. All right, and that's exactly what happens. You mix these two things together, you start heating them, and the kinetic energy of the reaction is going to start increasing. And at some point in time, you're going to break a bond. And the bond we would break first is the easiest bond to break. And we already know that covalent bonding is very efficient between carbon and hydrogen. They have similar electronegativities. They form very, very strong bonds. And here, maybe for the first time, we see about how strong it is, 100 kcals per mole. I think the text said 104, but 100 is a nice round number, easiest for it to have a grasp on what a carbon-hydrogen single bond strength is. On the other hand, we have chlorine and chlorine. These are two very electronegative atoms. They're fighting over those electrons in that bond. Each one wants them. And if we look at the actual covalent bond and what orbitals are used to construct it, they're p orbitals. They don't overlap very nicely. They don't form particularly strong bonds. And so this bond is very, very easy to break. So chlorine has poor overlap, and also it's very, very electronegative. And so the bonding is weaker. This discussion about bond strength and why, it's not really something you need to worry too much about. When I'm saying these things, it should kind of be in your head. You should be nodding along like, oh yeah, that makes sense. Chlorine is electronegative. If bonded to another electronegative thing, that bond's not going to be particularly strong. We know a lot about carbon-containing things. Our bodies are made up of them. Last time I checked, all my carbon-hydrogen bonds were pretty strong. They're about 100 kcals per mole. So we start heating this thing, and we've already figured out that the chlorine bond is the weakest one. It's the one that's going to break first. And there's two possible ways that it could break, right? And so here what we're going to think about is how/why Cl2 bond breaks. Kind of the why is we heat it enough it breaks, but there's two possibilities. The first possibility is heterolytic cleavage. And you should already know from the pre-lecture video which one actually takes place, but we're going to discuss it very briefly. But heterolytic cleavage, lytic comes from the word lysis, or cleaving, and hetero means uneven or dissimilar. Let's imagine that we heat this thing and the bond breaks using our double fishhook arrow, the way that we've been pushing electrons in acid-base chemistry. This means moving two electrons. And if we drew the result of this, it's going to be an equilibrium process we're going to see. If we drew the result of this, we break this bond, we give two of them to chlorine on one side. That's what we would get. And what would be left for the other chlorine? Well, this pair of electrons, this pair of electrons, this pair of electrons, nothing happened to them. There was a bond here, and this arrow says, well, let's just give it to this chlorine, and maybe that's this bond. Then this one's left with nothing. And we've basically made ions here. So this is the result if we were to heterolytically cleave the bond unevenly. Give two electrons to one atom, give nothing to the other. This is what we get.